Yeah, my dear student friends, I hope you understood the last class lecture, and I was talking much about the importance of a separation process. Maybe you feel that the course is of a mass transfer operation and we are talking something about a separation process. The separation process is applications of a mass transfer operations, and even in your courses mass transfer operations and 1 and mass transfer operation 2, and first few units or first few modules we are going to discuss about the importance of the transport phenomena in a mass transfer operation, but the remaining things we are going to discuss about the applications. So that is what I want to stress. I would like to explain the student the importance of the separation process, and I want to convince you without a separation process this mankind cannot sustain. And once if you understand this thing, then when one can discuss about what is mass transfer, how mass transfer is going to take place, how one can calculate the mass transfer flux, how it is related with your heat transfer, how it is related with your fluid mechanics, maybe how to carry out or how to conduct the mass transfer operations. All those things I would like to explain at a later stage of a time. So initially what exactly I want to talk again on the separation process, the importance of the separation process, why one should think about the separation process. So if there is no separation process, nothing is there. So that is where we were discussing about the separation process, different applications of a separation process, and I have given already several of the applications of a separation process, and in the last class we were discussing about the forces which are impacting the separation process, and today the customer wants a better product, a cheaper product, and at a faster rate, and that is only possible with you. With you means with the chemical engineering students, not with anybody else. And with this small introduction, I want to continue my previous class, and whatever the discussion that we have done earlier, whatever the thing that we are talking about, the above forces are leading to the utilization of multiple separation technologies for certain applications. We don't like to use the one separation technology, we want to use the multiple separation technologies. And innovations at a small scale, and increased use of integrated separation and hybrid processes, then improvement in the energy efficiency, creation of separation methods for the ultra high pure chemicals, development of separation process for the management of waste. And for example, when you talk about utilization of multiple separation technologies for certain applications, the same example whatever I given earlier, that is about ethanol water system, and we are getting your ethanol from the fermentation broth where it contains around 10% of alcohol, and that 10% of alcohol has to be increased to 99.8% or 99.7% alcohol. If somebody wants to use this alcohol for the fuel applications, maybe for a drug applications. If that is the case, what one has to do, you have to use the distillation, because distillation is a well-known separation technology used for the separation of liquid mixes. But as I told you already, distillation is unfortunately the system of water and ethanol forms an azeotrope at 95.6% concentration. We cannot use the distillation. We have to go for the azeotropic distillation and extractive distillation, where we are adding an extra component. When you add extra component, when you want to remove this extra component, then the cost of the process is going to be increasing. So instead of that, what one can think about now, a recent things what we are doing is use a clubbing of multiples of separation technologies, not one separation technology. As I told you already, distillation, azeotropic distillation or extractive distillation, or we can think about separation process, separation technology. What presently we are working at with our students is a peroperation process at initially, distillation in between, the peroperation again. Maybe I don't know whether you know thermodynamics or not by this time, but we talk something about a vapor liquid equilibrium. Maybe that is what you have learned something in the chemical process calculations. What is the concentration in the liquid phase, what is the concentration in the vapor phase. So if you know the liquid phase concentration, you know what is the concentration that we get it in the vapor phase. Now, and that is what we plot a graph between the liquid phase concentration and the vapor phase concentration, and that is what we call it as a VLE plot, vapor liquid equilibrium plot. When you look at this vapor liquid equilibrium plot, the vapor liquid equilibrium plot curve is so close to the 45 degrees line at low concentration. Again, it is very low at high concentration, and in between there will be distance is very large between the vapor liquid equilibrium curve and 45 degrees line. So when the distance is larger, we need a less number of stages. If the distance is smaller, we need a more number of stages. Maybe I don't know whether you understand what is the stage or not. And in the previous case, I have given another example. What I said, when you get a 10% of alcohol, when you vaporize it, we get around 20% of alcohol. Again, you condense it, vaporize it, condense it, vaporize it. So that is what we call it. Each one we are calling as a stage. And when somebody wants to get 99.8% of alcohol, maybe he needs around maybe 20 to 25 stages. So as the number of stages are increasing, the cost obviously is going to be increasing. So instead of that, what one can do, we can use the multiple separation technology. In the case of multiple separation technology, at a low concentrations of alcohol, that is at 10% of alcohol, you don't go for the distillation, you go for a technique called the peroperation. When you go for the technique like a peroperation with the hydrophobic membrane, with the hydrophobic membrane means because alcohol concentration is very high, water concentration is very low, it is better to remove the alcohol rather than removing the water. So when you use the hydrophobic membranes, the ethanol will pass us through the membrane and the water will not pass us through the membrane. And when you see on the other side of the membrane, we have a more concentration of ethanol and less concentration of water. Now you take that ethanol and water, now you subject it to the distillation. Now get around 90% of alcohol. Now when you get 90% of alcohol, and to remove the remaining 10% of water, we use the peroperation again with a hydrophilic membrane. In the case of this hydrophilic membrane, because the concentration of alcohol is very high, the concentration of water is very low, it is better to use hydrophilic membrane. It is better to remove the small concentration of water rather than removing a large concentration of ethanol. So what we do is we remove that 10% of water by using a hydrophilic membrane. So what I want to tell you, a combined technique called a peroperation, distillation and a peroperation will gives you your 99.7% of alcohol, which requires less energy. We are going to get some energy efficiency, and which we are going to use the multiple separation technologies, and that is what I told you, utilization of multiple separation technologies for certain applications. This is the one of the thing, the forces which are impacting the separation process is leading to use the multiple separation technologies for certain applications. Then innovations at a small scale. Innovations at a small scale, as I already told you about that fuel cell development at Japan by a small company which can produce 1 kilowatt hour. So they are doing everything, whatever the innovation they want to do, the innovation they are doing at a small scale, and that is satisfying the needs of at a smaller capacity. So what we want to do, we want to do the innovations at a small scale and increase the use of integrated separation and hybrid processes. We are, as I told you already, we don't like to use the one technology. We are going to use the multiple sub technologies when we make the process is the hybrid separation process. This is what I spoke to with you regarding the pulp and paper industry. When you get a black liquor, instead of using some other technique, we can use the membrane separation process where we have a ultrafiltration, nanofiltration and a reverse osmosis. So we are going to use a hybrid process and improvement in the energy efficiencies. This is what I told you. Instead of using a distillation and azeotropic distillation, distillation and extractive distillation, one can use the peroperation, distillation and peroperation. That will give you more energy efficiency. To tell you again small story again here, if I want to get 99.7% of alcohol, if I give this problem to American engineers, they design the distillation column not to get a 99.7% of alcohol. They design the distillation column to get a 99.8% of alcohol. When they do design for 99.8% of alcohol, that means excess design, whatever 0.1 extra concentration is there, that they do the excess design. When they do this excess design, the energy costs are going to be increasing by 13%. But if you give the same problem for the Japanese engineers, they exactly do the design for 99.7%. Why the difference is coming? As I told you, I think by this time you know a little bit about the process dynamics and control. You have a load variables, you have a manipulated variable, we have a control variable. Your load variable is, in the case of distillation operation, your load variable is you are getting alcohol and water, maybe a fermentation broth. There you cannot have any control to get 10% or to get a 9.9%. You are subjecting to the distillation. You use a fixed number of stages, and your thermodynamic says if you can use this many number of stages, and if you are going to use something like a reflux ratio, we are able to get a concentration of 99.7%. If something goes wrong, that is what we call it as a manipulated variable. If something goes wrong at a load variable, your final thing what we want is a 99.7%. You are not able to get a 99.7%. So what you have to do, we need a sophisticated control system. When you talk about a sophisticated control system, the distillate, maybe the product, the ethanol what we get at the top of the distillation column is subjected to a gas chromatograph. That is, we are measuring the concentration. If you are getting 99.7%, your control system will not do any changes. If it is not at 99.7%, an error is going to be generated. Based on that error, your controller will act on the final control element. In this case, the final control element is your reflux ratio, reflux valve, and this reflux valve, we are going to adjust the reflux valve in such a way that reflux ratio is going to be adjusted, and you are going to get your required concentration of 99.7%. And if you give the same problem as I told to American engineers, they don't do for 99.7%, they are going to do it for the 99.8%, and because of this 0.1% increase in the concentration, the energy cost is increasing by 13%. And a country like America, which is supported by so many, which is having a support from the Gulf countries and other things, energy is not a problem for them, and they can forego that 13% of energy. But a country like Japan, the energy is the most important thing. There is so much of scarcity is there for the energy, and they cannot go for this excess design problem. They cannot do this sort of excess design. Exactly, they are going to do for 99.7%. So that is what I want to tell you. You have to develop a sophisticated control system which can control things within no time, and you are going to get your product of 99.7%. Otherwise, the product what you are going to get it, there is no value for this product, and no customer is going to purchase. So there is improvement in the energy efficiencies and the creation of separation methods for the ultra high pure chemicals. That is, when you talk about the semiconductor applications, and we need high pure chemicals, and when you want to go for the high pure chemicals, we have to use some sort of a new separation techniques to produce this ultra high pure chemicals. To tell you one story, small story again, people talk a lot about the cool drinks. They say cool drinks is not good for the health. And the same cool drinks we were drinking maybe in 1960 onwards, but suddenly people started talking about there is a pesticide traces in the cool drinks, and one cannot drink the cool drink. But these pesticide traces are already there in the cool drinks even in 1960, but it's not new. The reason was, earlier the system is not so sophisticated. Your control systems are not sophisticated, or your measuring devices are not so sophisticated. If the concentrations are very, very small, that is not traced by the instruments, we are not able to get the concentration. But now, because of the developments on the electronic systems, electronics materials, we are able to develop some gas chromatograph. Maybe you are going to develop some advanced instruments which can give even concentration at the ppb level, parts per billion. So once we called as a good material, now it is becoming a waste material. Even if that is there, if you don't like to drink a cold drink which is having a concentration in terms of ppb, what one can do, we can use some separation process where we can remove that low concentrations of pesticides, and we can provide a cool drink which the customer wants. So we need to have a creation of separation methods for ultra high pure chemicals. This is what even semiconductor applications are. If as already I told you with the case of hemodialysis, in the case of hemodialysis, we are preparing the dialysate. And for the preparation of the dialysate, we are going to use the low molecular weight solutes as well as the water. If the water contains impurities, when you contact your blood and the dialysate, whatever the impurities that are present in the water will now pass into the blood. Instead of blood getting purified, the blood getting impurity. So what we need is high pure waters are required. So just to tell you a story about the water, when you take water from the well, the cost of the water may be around 2 to 3 paisa per 1 liter. But when you want to use the water for the drug applications, the cost of the water may be 1,000 rupees. And what is happening here? During this process, we are going to use a series of separation process, maybe a 16 to 17 unit operations we are going to use, and we are going to get the pure water. And as the concentration of as we need a pure water, the cost is going to be increasing. So what you have to do is we have to create some separation methods. Like as I told you, 17 unit operations. What they do is initially they use some primary settling, that is some sort of a sieve they use. If any suspended solids are there, that will be settled and water will pass. Then this will be passed into the biological operations. There we remove organics and other things. Then it contains the inorganics. We are going to use a series of ion exchange, series of reverse osmosis process to get a ultra pure water. So what I want to tell you, if the membrane what we use in the reverse osmosis process is a good membrane, then the cost of the product is going to be decreasing. So there is a need to create a separation methods for the ultra high pure chemicals and development of the separation process for the management of the waste. So we are going to generate lot of waste, and if you continue to generate this waste, and maybe tomorrow generation they will not find any space for throwing of their waste. Forget about for throwing of their waste, they don't find any space for the living purpose. So this is the one of the major issue, and what you have to do is we have to use the waste for generating some useful materials. So what one has to do, we have to develop some separation process for management of waste. So these are what are the forces that I told you, the above forces imparting and the above forces are leading to, these are the things. So maybe it is a good time for you to look at this course and to understand about the applications, and when you go through these applications, you yourself feels there is so much of scope is there, particularly in the area of separation process, in the area of chemical engineering, and I can assure you that you can do wonders in the life. And just to spend one more minute on this thing, management of waste streams. As I told you, the toluene water system. If you take any petrochemical industry, the water which is coming from the petrochemical industry contains a toluene, maybe contains a benzene, maybe contains a xylene. And if when water is alone, there is no problem for the quality of the water. If the toluene is alone, there is no problem for the toluene. But when the toluene and water are mixed, in the presence of the water, the activity of the toluene is going to be increasing. When the activity of the toluene is increasing, it creates irritating smell. And when it is creating irritating smell, and we cannot use it that water for the drinking purpose. In the presence of water, the activity of the toluene is increasing, and when the toluene activity is increasing, we cannot use it for the drinking purpose. So what we are doing is we are generating some waste, and if you continuously generate this waste, and someday, as I told you already, there will not be any space tomorrow to store this waste. So what today people are using, you are using a technology called as maybe a carbon adsorption. Maybe people are using a stripping process, people are using the peroperation process to recover or to separate your wastes, so that you can use this waste. And another example, as I told you, in the case of pulp and paper industry, we are getting a waste in the form of a black liquor, and we are using a series of membrane separation process, and we are going to get a lignin as the byproduct, and this lignin can be used as some sort of a adhesive. That is what we are trying to do, is we are trying to do the management of the waste. And by this time you understand that there are several of the separation processes are there, and for even same product, to get a same product, you did not use a one separation process, we can use a series of separation process. For example, as I told you, the same example of ethanol and water system. When you talk about the ethanol and water system, we have ethanol and we have water. So we can use the distillation. We can use the azeotropic distillation, we can use the extractive distillation, we can use the liquid extraction, we can use the adsorption, we can use the peroperation, we can use the crystallization. So obviously when customer comes to you and says this is the solution I have with me and what is the separation technology that I have to use it, so immediately you are going to get several of the doubts which technology you have to use it. So there are several factors which are influencing the, and that means you have to select the separation process, and what are the factors that are influencing the choice of the separation process is the feasibility, is the product value and the process capacity, and damage to the product, separation factor and molecular properties, chemical complexing, and experience. So these are the factors that one should look at, and obviously as I told you already, the feasibility is the most important thing, and most of the screening of a separation process can be accomplished on the basis of the feasibility alone. And as I told you, we have a technical feasibility, we have a economical feasibility. In the case of technical feasibility, one has to look at whether when somebody comes and asks you, you have to look whether technically it is feasible or not. To tell you one thing, suppose if I want to separate the isomers, if I want to separate the azeotropes, if I want to separate the maybe substances having the same evaporations, I cannot use the distillation. So the technically is not possible. When the technique is not possible technically, there is no point of thinking about a economical feasibility. So what we have to see when you are selecting a separation process, we have to look at two things. The first thing is the technical feasibility, whether technically a given separation process is feasible or not. If it is possible, then we have to think about the economical feasibility. If economically feasible, then you have to select a separation process. For example, suppose if I want to separate non-ionic organic, maybe I can give you one other example. People talk about a pitch blend. This is a mixture of uranium isotopes, uranium 235 and uranium 238. And when I have these isotopes, when I want to separate these uranium isotopes, I cannot use the distillation, even though I know that the energy requirement, the cost requirements, and so many things by distillation is cheaper when compared with the other separation process. But thing is, I cannot use this separation of uranium isomers, uranium isotopes by distillation, because these uranium isotopes are having the same vapor pressures. You cannot use the distillation. So what is the technique today people are using? Separation of uranium isotopes by membrane gas separation. And here also, when they talk about the membrane gas separation process, they are not getting a good selectivity or a good separation factors. But even today, there is no other separation technology other than the gas separation by membranes and for the separation of uranium isotopes. Just if you look at the uranium isotope separation plant, there will be around 300 to 400 stages will be there, and you will be going through some sort of a corridors, right? And that is what very interesting applications one can see. Then similarly, acetone diethyl ether, we cannot use the ion exchange process, we cannot use the magnetic separation, we cannot use the electrophorus, because there is not much difference in those aspects. We cannot use the foam separation or bubble fractionation, because there is not much difference in the surface activity. We cannot use the leaching, we cannot use the freeze drying, or we cannot use the zone melting. It requires a solid free and needs extreme processing conditions. So what you have to do in the case of leaching, one of the material is a solid. What you have to do is acetone and diethyl ether, these two are the liquid mixers. Reduce the temperature, convert the liquid into solid, and once if you convert into solid, then we add a solvent, you can go for the leaching. And going to such extreme processing conditions is very, very difficult. That is the reason we never think about a leaching process to separate the acetone and diethyl ether. So similarly, a mixture of many components is to be separated into the relatively few different products. Example, a separation of mixture of propylene and propane and propydiene. Distillation, if you are going to use, we are going to get the propylene as the top product, other two are the bottom products. If you are going to use the extractive distillation, and if you are going to use the polar solvent, we are going to get the propane as the top product. And if you are going to use the extraction with the polar solvent, and the propydiene, it comes to the other side, and we are going to have the propylene and propane. So what I want to tell you, if I have a mixture of propylene, propane and propydiene depends on the what is the desired component per you. Either you can select it a distillation, you can select it a extractive distillation, or you can select it a extraction with a polar solvent. So that is the feasibility is the most important point one has to look at that. Then the separation of aromatic hydrocarbons. I think many of you know today there is a challenging task for the separation of aromatics and aliphatics, particularly C5 to C12 compounds. When you talk about the C5 to C12 compounds, or maybe when you take a crude petrol, when one of the stream you are going to get it that contains a C5 to C12 of aromatics as well as the aliphatics. And when you want to have a pure forms, what will happen? There is a overlapping of the boiling point temperatures. Because of the overlapping of the boiling point temperatures, we cannot separate it by a distillation. And you can use it as extractive distillation, or we can use it as a extraction. And for feeds of very wide boiling range, extractive distillation and extractions is better. Low molecular weights, extractive high saturates, for the extraction we can use it. And this is what I told you already. The product value is the most important thing. What is the product that we are going to get it? What is the value of the product? Based on that you have to select a separation process. To tell you one small example, cleaning of a clothes, and particularly silk saree. And I mean, what we can do, we can take a silk saree, we can wash it, and after washing it we have to remove the excess water. And if you want to remove this excess water, what you have to do, you have to squeeze it. When you squeeze it, the water, whatever it is there in the cloth, will expels, and you are going to get the saree. But you have squeezed it, by that time your saree gets damaged. Your product is getting damaged. Your product is a high value saree, and you are using a technique called as a squeezing, and because of this squeezing the product is getting damaged. So that is the reason what we do is we can go for the technique called as a drying operations. In the case of drying operation, we have a saree, and we have to wash it, and we are not going to wash with the water, we are going to wash with some organic solvent. That is what we call it as a dry cleaning. And when you do the dry cleaning, cleaning is a dry cleaning, so you use some organic solvents wherever this mud and other particles are there, and that will be transferred to the solvent layer, and finally your saree contains some amount of your organic solvent, maybe some amount of little here and there. So what we use technique called the drying, where we pass the dry gas. When we pass the dry gas, whatever these organic compounds that are present, and that is nothing but a methylene chloride, and that methylene chloride will be transferred to the gas phase, and you are going to get the saree which is of a there is no damage to the saree. And this is what I told you, the product value is the most important thing, and based on the product value you have to choose the separation process. And many separation process which would be suitable for substances with a high value cannot be considered for substances with a low value. And another important factor that we have to look at is the, and just to give you one more example for the product value, nowadays everybody talks about what do you call it, oil, refined oil. And as you know how you are going to get the oil, maybe a groundnut oil, we use it for the cooking purpose. We have a groundnuts that contains oil, and what we do is we do the crushing. When you do the crushing, the oil will be expelled, and now that oil will be there, oil and your cake will be there. We use the filtration. When you use the filtration, the oil will pass us through the filter cloth, and you are going to get oil. The quality of the oil is not that good, and if you want to sell this oil, maybe places like Banjara Hills, where it is not possible to sell this oil because the customer is expecting for the high value product. Then alternatively, one can think about a leaching process. In the case of leaching process, we have oil seeds. What we do, we contact with the hexane solvent. When you contact with the hexane solvent, the oil is having affinity with the hexane solvent. The oil will be transferred to the hexane layer, the impurities are going to be left over. Then now you do the filtration, the impurities will be left over, oil and hexane will pass it through the filtration process, filtration unit. Now then you can go for the distillation. When you go for the distillation, the hexane is the high volatile substance, or what we call it as the low boiling substance, that will be coming as the top product, and your oil is having a high boiling point temperature or low volatility will come as the bottom product. The quality of the oil is a very, very good, and this oil, that is what we call it as a double refined oil, single refined oil and triple refined oil, and people who want to have a good quality oil, they will purchase this thing. And at the same time, you want to sell this oil, maybe go to the village where people are very poor, and when you want to sell this oil, nobody is going to purchase. So what you have to see is what is the product value. Whether you are selling this product to the rich people, people who expect high quality, whether you are selling this product for a poor people where people are not worried about the product quality. So based on that, you have to select a separation process. If you want to have the low quality product where the price is less, you have to use the crushing and filtration. And if you want to have a high quality product and high cost also, then what you have to do is you have to go for the leaching, filtration, then you have to go for the some sort of a, what do you call it, distillation. So in both the cases we are going to get the groundnut oil only, but thing is, there the cost of the groundnut oil may be 40 rupees when you are going to use the mechanical operations like crushing and filtration. When you go for the mass transfer operation, the cost of the oil may be around 80 rupees, 90 rupees. So whatever that 50 rupees what you are spending, this 50 rupees you are only spending towards your separation technique that we are going to use. So this is what I told you when maybe as I told you, nowadays you find so many mineral water plants everywhere. Somebody is selling at 20 rupees, somebody is selling at 50 rupees, and sometimes we feel that maybe this fellow is trying to cheat me and this fellow is selling at a lower price. That is not the right thing, because there they are going to use some good technology, maybe a good reverse osmosis membrane. Here this fellow may not be using a good reverse osmosis membrane. That is the reason the product quality is less. Because the product quality is less, obviously the cost value will be less. So what I want to tell you, the product value is the most important thing. And similarly, the process capacity is the most important thing. What you have to see, whether you are working with the grams, whether you are working with the kgs, million kgs, whether maybe you are working with a milligram, whether you are working with a million kgs. For example, when you want to separate ethanol and water, if the ethanol concentration is very, very small, if I want to separate ethanol and water, the quantity of ethanol and water is very small, let's say maybe 1 milligram. So I cannot use the distillation. If I can use the distillation, whatever 1 milligram is there, that will be sticking to the walls of the distillation column, nothing comes out. Whereas you can use the chromatographic technique, and when you use the chromatographic technique, nicely we can separate the 1 milligram your raw material that contains ethanol and water. Maybe 0.1 milligram of ethanol you may get, 0.9 milligrams of water may get. But at the same time, when you look at million kgs of ethanol and water, you cannot use the chromatographic technique, and we have to go for the technique, maybe a distillation, maybe you have to go for some other technique. So what I want to tell you, the plant capacity is the most important factor, and based on that we are going to select the separation process. And a process for the manufacturing of a substance with a low economic worth per unit quantity will most likely be a larger capacity process. And if cost is less, means the capacity is larger. So based on that, one has to select the separation technique. So damage to the product, this is what I told you already, and sometimes we are going to, there will be damage to the product, and when there is a damage to the product, and one has to consider about this damage. As already I have given you an example where I spoke with you about the artificial kidney and lungs are damaged by the heat and addition of a foreign substances, and that is what I told you. If you are going to use the impure water and your product gets damaged, that is your blood gets damaged, because the impurities are transferred now from the dialysate chamber to the blood chamber. And at the same time, as I told you about the dairy industry, when you talk about the dairy industry for making of a milk powder from the milk, and if you are going to use a technique called as evaporation, when you talk about evaporation, the boiling point, if you are going to conduct evaporation at 1 atmospheric pressure, the boiling point temperature of water is 100 degrees centigrade, your milk gets damaged. So avoiding damage to the product can be a major consideration in the selection of a separation process, and thermal damage may be manifested through the denaturation, formation of an unwanted color, polymerization, etc. That is what presently we are working with a topic on lactic acid. When you are working with the lactic acid, and if you are going to do the lactic acid separation at using a distillation, there is a formation of a polylactic acid. So if I am going to get a that is what I talk about a polymerization. If I get a polylactic acid, there is no use of that polylactic acid. So what I have to do is, that means there is some sort of a thermal damage is taking place, and I don't want to have such type of thermal damage. So to avoid such type of thermal damage, what you have to do is, we have to do the distillation under vacuum. Maybe we have to reduce the hold up times in the reboilers. Maybe what you have to do is, instead of using a energy separating agent, one can think about the barrier separating agents. And thermal damage can be minimized by using a well chosen freezing condition, and freezing can also be irreversible damage to the biological materials. To tell you, this is again a small thing. I don't know how many of you know about the liquid nitrogen. The liquid nitrogen temperature is around minus 194 degrees centigrade. If you take a rubber tube, and you know how flexible that rubber tube, and if you keep this rubber tube into the liquid nitrogen, and when you take out this rubber tube, and after keeping some time in the liquid nitrogen, when you take out this rubber tube from the liquid nitrogen, this is no more a rubber tube, this will be like a steel rod. So what is happening? Because we are doing some sort of a freezing, because of this freezing, and that tissues maybe that polymer materials get damaged, and permanent damage may be occurring in some cases. Even that is what I told you, and particularly when you talk about maybe storing of maybe something like liquid nitrogen falls onto your body, and we have a biological tissues in body, and this biological tissues gets damaged. So the separation technique that we are going to use, so there is no such type of damage to the product. And the separation factors, and maybe we can discuss more about the separation factor at the later stage of the coursework, because we have to discuss something, what is separation factor, what is the stage now, what is the stages and other things. But thing is, the separation factors are going to play an important role. That is what I told you. When I want to separate the uranium isotopes, if I want to use the distillation, the relative volatility or the separation factor is only 1, and I can't use the distillation. Whereas if I talk about the gas separation by membranes, the separation factors are only 1.014. Even that 0.014 is attracting the people to use this gas separation by the membrane, membrane gas separation for the separation of the uranium isotopes. So if the more is the separation factor, cost will be the less. So what you have to see, what you have to choose, maybe for example when you talk about the acetic acid water separation, and I think many of you know about the vinegar. Vinegar is the 4% of acetic acid, and when you want to separate this vinegar and water, one can use the distillation, but when you go for the distillation, there is a strong bonding between your water as well as the acetic acid. The relative volatility is very, very small. Instead of using the distillation, instead of going for the distillation, one can think about using the what do you call it as maybe liquid extraction using a benzene as the third solvent, maybe liquid extraction, maybe a chloroform as the third solvent. So that will be the better. So what we have to see is we have to see at the separation factors, and these separation factors are going to depend on the Lennard-Jones collision parameters, and this Lennard-Jones collision parameters already you have undergone in your chemical process calculation when you are reading about the vapor pressure, when you are talking about attractive forces, and when you are talking about the repulsive forces. So this is going to depend on the several things. Just I would like to leave this as a material rather than discussing with you, because it's too difficult for you to understand at this moment of time to understand about the separation factor. But this will be an important slide for your future studies. because you have studied so many things in the physical chemistry, you have studied so many things in the thermodynamics. Maybe we talk about dipole moment, maybe polarity, maybe polarizability, maybe Lennard-Jones potential. So all those combinations we are going to use for the selection of the separation process, where the selectivity or this separation factor are most important thing. The selectivity or the separation factor, or what you call it as these are going to depend on the molecular shape, and this is going to depend on the dipole moment, this is going to depend on the polarizability, and this is going to depend on the dielectric constant, this is going to depend on the Lennard-Jones potential. All those things are going to make you to calculate the separation factor. Based on that we can select a separation process for a given application. And above all, the experience is the most important thing. When you talk about the experience, right, I know that a particular separation process is good for separation of a given material, but I don't have any experience with that separation process, and then there is no point of talking about that separation process. So development of a new separation process necessarily requires research and laboratory scale testing. And maybe this is what I told you. I did my PhD in the area of per operation process. I know that this per operation process will work nicely for the separation of liquid mixtures. But suppose if you want to, if an industry wants to use the per operation technology for the separation of liquid mixtures, alternative to the distillation, they need somebody who is expertise in that area of per operation process. But it is so difficult to find the people who works in the area of per operation process, because it's not a conventional process, it is a non-conventional process. So the experience is the most important thing. And ultimately, whatever the thing you talk about, all these things, the experience is the most important thing. And if you don't have experience in a particular area of separation process, one should not select that particular separation process. So to tell you some examples, as I told you already, the technical feasibility is important, the product value is important, the process capacity is plant capacity is important, the selectivity is important thing, the experience is important thing. For example, if somebody wants to separate the water and sodium chloride, this is so common substance, or the common solution everybody knows, and we can use the evaporation, we can use the crystallization, we can use the reverse osmosis, and we can also use the electrodialysis process. So as I told you already, when you are going for the evaporation process, and we have to give lot of energy, and you can go for the crystallization, and we are going to get a nice crystals, and we can go for the reverse osmosis. On one side, when you go for the electrodialysis or the reverse osmosis, one side you are going to get the pure salt, other side you are going to get the pure water. So whether you are going to select evaporation, whether you are going to select a crystallization, whether you are going to select reverse osmosis or electrodialysis, it depends on the application what you are looking at. Then we have a separation of acetic acid and water mixture. As I already told you, the acetic acid is one of the important organic compound other than the ethanol, and 4% of vinegar, as I told you, 96% of water we have, and the acetic acid boiling point temperature is 118 degrees centigrade, the water boiling point temperature is 100 degrees centigrade. Even though there is a large boiling point temperature difference is there, one cannot use the distillation because there is a strong bonding is there between the acetic acid and water. So, and at the same time, water is a more volatile component in this case, acetic acid is the less volatile component, and as you know, the water which requires a large amounts of latent heat of vaporization when compared to the organic compounds. So when you go for the distillation, we have to evaporate the water, you have to give large amounts of the latent heat of vaporization. So your distillation may be technically feasible, but economically it is not a feasible technique. Similarly, when you talk about the liquid extraction, we can use the liquid extraction technique by contacting acetic acid water mixer, maybe with some toluene, maybe with some benzene, or maybe with some other compound. Then we can use the adsorption, that is you can take some adsorbent, maybe the adsorbent is having affinity either with acetic acid or the water, so one component is adsorbed and other component will pass through the adsorption zone, and then we can do the regeneration. That way one can separate the acetic acid and water. So you can also use the per operation. This is what I told you already, a membrane separation technique that is used for the separation of liquid mixtures, and there are so much of research is going on in the area of per operation process, but still it is a infancy state, and there are several separation techniques we have for the separation of acetic acid water. Similarly, as I told you, volatile organic mixtures from the water, we can use the stripping, we can use the adsorption, we can use the per operation, we can use the liquid extraction, we can use the reverse osmosis. Each technique is having its own advantages and the disadvantages. Which one we are going to select it, that depends on the factors what we have discussed earlier. So as I already told you, there are so much of literature is available on the separation process, and there are newer technologies are coming, new separation processes are being developed, but still this Vision 2020 separations roadmap that is developed by ASEH, American Institute of Chemical Engineers, for advanced waste management in cooperation with the US Department of Energy. They want to work on the adsorption, and in this case they want to work with new adsorbent materials. They maybe want tools to predict the adsorbent performance. They want to understand the physical phenomena lying on the adsorption. And see, thing is, every material can be used as adsorbent materials. Even waste can be used as one adsorbent materials. Now we have so many adsorbents, and these adsorbents may be good for a separation of a particular materials. So many of in this now presently the whole world is working on the adsorption process to identify the new adsorbent materials and tools to predict the adsorbent performance. Obviously, when you select adsorbent, the next question is how good this adsorbent, and we have to predict that adsorbent performance. Then we have to see about the better understanding of the physical phenomena. As you know, maybe already you have studied a little bit about adsorption process in the physical chemistry. We have a monolayer adsorption, we have a multi-layer adsorption. We have adsorbent site is there, already one material is adsorbed, maybe the next material will adsorb it, may not adsorb, that depends on the adsorbent and adsorbate, and adsorbent, adsorbate, adsorbate. So then the next thing is, people talk about the distillation is a very old technique, nothing can be done in the distillation, but there are so many new areas one can work in the distillation operation. There may be a predictive modeling tools, maybe new materials, enhanced operability and robustness, structured packing. This is what we are going to discuss at a later stage of a time. To conduct any separation process, we need some sort of a vessel, and that vessel we call it the packet towers. In the case of packet towers, we have a random packing, we have a regular packing. In the case of random packing and regular packing, each one is having its own advantage and disadvantages. So people, they want to work with a structured packing, particularly when they want to have a less pressure drops. When they want to have a less pressure drops, they want to work with the structural packing. Then another area where people are looking at now is the membrane separation process. In the case of membrane separation process, as similar to the adsorption, new adsorbent material, here is the new membrane materials and compact modules. The module size should be as small as possible, but it should give the larger area. Then better predictive models. Then one more area where people are now working on the electrostatic interactions in protein transport in the membranes. This may be hybrid process for the removal and recovery of the VOCs, maybe. And what is the thing that is now going on? There is the rapid development in the material and computational schemes. Earlier, even though, as I don't know how many of you know, this is chemical engineering is highly nonlinear, and when it is so highly nonlinear, the equations what we are going to get it highly nonlinear equation. When it is so highly nonlinear equation, the computational schemes that are available in the olden days are not good to solve this highly complex equations, highly nonlinear equations. But so much of things are going on in the area of mathematics, particularly in the area of computational area. So even the equations are very complex. One can solve these equations, and your design may be very close to the actual design. It will fuel the new waves of inventions and innovations in the separation process. What I want to tell you, the material technology, new materials, new computational schemes are providing a platform to do innovations and the inventions in the separation processes, and these are further fuel new strides in both an industrial and environmental quality control. And as what I can tell you, there are new challenging and exciting times to separation communities in future. And this is what I want to tell you, the importance of the separation process. Maybe I understand it is so difficult to understand about the this many separation process at this stage, but the thing is, unless otherwise you don't understand the importance of the separation process, you don't enjoy the course of mass transfer operations. So what I want to tell you, you can, whenever you get an opportunity, or whenever we are going to see what are the applications of a mass transfer operations. There are several of these operation techniques. Even when you talk about public, they will be coming with some problem, you should in a position to solve it. So there are several of the challenging problems are there, and maybe a simple case about LPG separation. It contains propane, propylene, and a mixture of propane and propylene. That is nothing but you have to separate this propane and propylene, and the separation of this propane and propylene is not so simple task. That means alkanes and alkenes, we have a mixture of alkanes and alkanes, and there is a overlapping of the boiling point temperatures. Because of this overlapping of the boiling point temperature, we are unable to separate the alkanes and alkanes, and because of this, we don't like to use either propane or propylene. We are going to use the mixture of propanes and propylenes. So there is a challenging times and exciting times are there for the separation communities. So what I suggest, maybe this will help you to follow thoroughly about your course on mass transfer operations. So what we have, we can divide the total syllabus into the 8 modules. These 8 modules we may cover around 35 to 36 classes, and out of these 35 to 36 classes, in first basically 4 modules, maybe 5 modules basically consists of a transport phenomena in mass transfer operations, which is similar to the heat transfer and a fluid mechanics. Suppose if you have a good experience and knowledge in the heat transfer and fluid mechanics, it is so easy to understand the first 5 modules of your mass transfer operation, and the remaining 3 modules is basically the applications of a mass transfer operation, that is nothing but a separation process, whatever we are discussing now, that is about drying, humidification and absorption process. So then this whole thing we can cover in 35 to 36 classes, and whatever the syllabus books, very good book written by mass transfer operations by Tribal is there. Then Principles of Mass Transfer and Separation Process by Indian author, that is the B.K. Datta, which is one of the very interesting and good book. And other than this, we have a Giancopoulos as well as the Cedar and Henley. So whichever you like it, you can follow, but mostly I will following the Mass Transfer Operations by R.E. Tribal, which is the 3rd edition of McGraw-Hill Publishers. So thank you very much, and we'll see next class. Thank you.